Pleasure to introduce today's speaker, Professor Harshan Jagadeesh. He will be speaking on leveraging analog codes for privacy and robustness in federated learning. Professor Harshan is an associate professor with the Department of Electrical Engineering, IIT Delhi. His research interests lie in the broad area of network security with a special focus on applying information security techniques to communication, storage, and computing systems. Over to you, Professor.
Perfect. Thanks. Is it okay? So if I say, so right is backwards. This is front. No. Turn. No. Wow, it's there's a bit flip happening actually. So there's something wrong. So let's hope that it's continuous, consistent manner. Okay. Maybe I'll just give it a try. Let's see. I will probably drag this far away so that I could stand at one place. Oh. Good to go? Okay, great. Hello everyone. Thanks for joining. Thanks to the CNA group for arranging this talk. I'm going to talk about some problems related to privacy and robustness aspects in FL, Federated Learning. These are some recent results from our group at IIT Delhi. This is joint work with my MSR student, Mr. Usaid Shahul. Part of these results have appeared in ITW 2025 last year. So, FL has been here for a while, Federated Learning. But still, just to set the context, I'm going to give a quick overview of what it is. So this is a setting where, imagine there are nodes that have compute power. So they want to run a sort of a common interest task, mostly for inference or signal processing or analytics, and with the intention of running some kind of a data-centric model for which they need data sets to train their model, right? So individually, they are sitting with some data set, but then if they choose to train their models using their own data set, then probably that's insufficient to have a good model standalone. So therefore, under those scenarios, FL has been an excellent paradigm where it allows the nodes with a common interest to collaborate, cooperate, and then exchange their models in such a way that they end up with a really good model with two things, with insufficient data at their sides, as well as maintaining some amount of privacy because they don't really reveal data sets to the other users, right? So for these reasons, it's got interesting use cases. In the so-called cross-silo setting, the FL users are institutions, infrastructures. For example, these could be hospitals which would like to run AI-based models for diagnosis, right? And then they may have insufficient data and they may want to take the help of other hospitals which have better data sets through FL. Other examples of use case could be, let's say, banking institutions for fraud detection and many other use cases as listed here. The other set of interesting use cases, they come under so-called cross-device settings. So here the users are not institutions or infrastructures, but these are sort of lightweight devices. It could be mobile phones, laptops, or any edge computing devices, so which have the capability to sort of do inference as well as training. For example, you have these health and fitness apps, mobile photography, and so on, which have a common interest for inference. They may actually train among themselves to get better models. Other use cases, very popular, also involve vehicular networks, where vehicles are the users, and then for maneuvering on the road, they may want to use their models, and then they may have insufficient data, because of which they may want to perform FL, right? So these are some very interesting use cases because of which FL has sort of seen very impressive progress in the recent past. So as such, for the outline of this talk, I'm going to focus on something else. So I'm going to look at how to implement FL in the scenario of untrusted environment, okay? So this is where, this is given that it's a distributed system, you have multiple users coming in. You may not have a good profile of them. So which means you have to be aware of these scenarios as well. In particular, we are going to look at two things, two aspects. One is privacy leakage. The other one is the impact of what's known as Byzantine threats. So these are malicious nodes. I'm going to get into details eventually. And a specific question I'm interested is to figure out how to handle both these features simultaneously. So these are sort of different features in security, but I want to have both these features of figuring out how to have more privacy along with resilience to Byzantine threats. So I'll cover that, and then I'll give you a quick overview of the contributions. So a couple of points to note is that I want to sort of convince you that analog codes from the field of coding theory has a very interesting role to play in this problem of giving privacy and Byzantine resilience. So I'll make a connection to that. And then subsequently, there's a deeper question of how to use analog codes for outlier detection for Byzantine resilience. So I'll give you an overview of contributions. That should basically capture the gist of the talk. And then for other details, we'll get into our framework in detail step by step, giving all the mathematical details. So we call our framework as FORTA. So that's based on Fourier technique. So that's basically, I'll run through this in the last few minutes. And then some results, and after that, I'll probably open the floor for some discussion. Okay, so quickly for some of us who are not well with FL. So this is a setting where you have a set of users. Each of these users have data sets with them. Data sets are not sufficient to deploy these models. So what they do is basically they take the help of a third-party server who is trusted. So basically, the truster starts with the initial model, sends that to the servers, sends that to the users. Users train this model using their data sets for a few epochs, and then they return it to the server. Server does what's known as aggregation of these model parameters, and then again returns to the users. Users again repeat their epochs, and then this process continues for a while. These are well-known things, right? But then theoretically, if some of the parameters are chosen well, then it is well known that eventually they end up with a global model that is very close to the stationary point or the global minimum points of the global loss function, despite not having the data sets. Right? Although they don't have data sets and they have not seen data sets among each other, they still are able to achieve so close to the stationary point. Right? So in a trusted environment where all the users obey to the right things, it's a fantastic paradigm. It gives amazing models. But then, given that we are looking at untrusted environment, one of the issues is the presence of malicious nodes. Okay? So who are these nodes? Let's refer to them as Byzantine nodes. These nodes are some of them, preferably smaller fraction of the participation. What they could do is they could basically inject noise during the update process of FL, okay, in multiple ways. One typical way is typically known as called model poisoning. What they do is when they train their model, the data sets that are used possibly are irrelevant to the task at hand, because of which the updates are also sort of irrelevant, and then that may basically drag the global model to a different direction, right? Or these malicious nodes can also add noise to the updates just before sending it to the server, right? So either way, there are many ways to spoil the show, because of which as the iterations progress, then the eventual global model that they get could actually have very diverging results, right? And then this is something that we don't want, because that's not the purpose of doing FL. But then, given that it's a distributed setting, we still have to be aware of the presence of these users and figure out a mechanism in which we have to sustain or sort of be robust to their presence, okay? So that's basically one class of problems people have been interested in. And to solve this, typically what they do is they piggyback on these well-known outlier detection methods from the signal processing community. So what happens is that once the server receives all the updates from the users, right? So it takes a look at all the updates, and then depending on some structure, distribution, and so on, depending on the use case, it tries to identify something that looks anomalous in terms of different from others, and then tries to discard it, and then only aggregate using the rest of the updates that appear honest, okay? And then continues the process. The point to note here is that we are not stopping the Byzantines to sort of to continue, right? What we do is let the Byzantines be there. I know that let the system have this many percentage of Byzantine malicious, but in the aggregation rule, I ensure that I aggregate in such a way that I only take the good users and then do it continuously, so that some amount of benefit can be obtained because FL, we want to do better than the standalone models, right? So that's typically the area of research with Byzantine users. On the other side, let's look at the other side of the coin, which is privacy, right? So although users did join FL because they only had to share the updates, but then eventually research in this area showed that even if these updates are made public, right? So one can reverse engineer these and then infer something about the input data, right? And which meant it's basically a privacy issue for someone who is not ready to sort of reveal all this information, right? So how do we solve this problem? Then we'll have to somehow share the updates to the server in such a way that no other user will be able to read it, nor the server should be able to read something into it, but yet the server should be able to aggregate the whole thing and then get the benefits of FL, right? So how can this be handled? So there are many ways. There's a family of solutions available from the theory of security. One could basically fall back on crypto primitives, very traditional, but unfortunately it doesn't really allow us to do compute on it. There are very interesting methods using secret sharing methods, right? So these are really appealing if you have a set of colluding users, which means more than one user is sort of willing to look into the updates of some users. But then the drawback is that it may require some knowledge of secret keys as well as a bit of communication overhead, right? The other sought after option is to do homomorphic encryption. Excellent option because once we encrypt the updates, the averaging as well as everything can happen on the ciphertext. But the downside of this is that it's at this point in time it's extremely heavy in compute. So this is not most sought after unless the area stabilizes with some amazing results. And very recently, I think people have been interested in applying differential privacy techniques where they sort of tend to add controlled amount of noise into their updates in such a way that they still have an accuracy that is with acceptable degradation, right? So this is some sort of relaxation of the original information theoretic security. These are the sort of family of methods available for taking care of privacy, right? So with that, we are going to come to the motivation of this particular talk. So what we're interested is that we are interested in achieving both, okay? We want Byzantine resilience and also privacy on the updates, okay? So which means there is a sort of family of options available on the left-hand side for Byzantine resilience. On the right-hand side, we have options available for providing privacy, but then maybe there is a way to sort of marry these two methods in such a way that these are implementable with affordable complexity and still get the benefits of FL. That's basically the theme, right? So how to have really these two classes of methods go together to achieve both the benefits, right? So maybe there are many ways to achieve this. There are pros and cons for each of these cases. But as a starting point in this direction, I'm going to pick one outlier method on the left, which is based on distance-based technique. There's something called as Krum or multi-Krum methods, right? So I'm going to pick that from the left. On the right-hand side, I'm going to pick something based on secret sharing. And then hopefully by the end of the talk, I'll convince you that by using these two methods, there is a way wherein we can actually have both Byzantine resilience as well as privacy. Okay. All right. So moving forward, I think given that we have picked Krum as a strategy for the Byzantine resilience, let's quickly revisit how does it work. So there are updates coming in from multiple users. Let's assume that F number of Byzantine users are there among the n of them, right? And the updates from the Byzantine users could be arbitrary and unconstrained. The way Krum algorithm functions is as follows. So basically what it does is it collects the model parameters from all the users. I'm going to denote this as WIs. So these are vectors, right? So you vectorize the model parameters and you give all of them to the server. What the server does is basically it computes pairwise distance between every I and j, right? And then you sit on one particular user and then look at its nearest neighbors in terms of distance, and you add the distances of all the nearest neighbors, right? Up to some of them. You have a count on that. And likewise, you do with everybody, and then finally pick the ones that have the smallest distances, a group of them, right? So essentially what happens is you are essentially picking a cluster of users who sort of look similar in majority, and you discard basically all those that are far away from the cluster. So that's basically what is depicted here in the red, right? Point to note is that for the Krum to work, it just needs pairwise distances between every I comma j, okay? And once this is given, then it will magically perform, and then we'll be able to figure out a subset and then aggregate based on this particular rule. Okay. Now, the score is for each user, yes. So you score for every I, right? And then choose the minimum one because that appears to be among maximum of others. One, you take that out, do one more round. This is single round Krum. And then you can do multi-Krum where you keep doing it, and then by the end of it you collect a group of them. That's going to be a subset. So if you're conservative, basically you can actually pull back a bit about n minus f minus 2, or you can go up to f. So but here also the assumption is you know f. Yes. So you don't know exactly f, but then you have a bound on f. You say 20% are, and then you work with that rule. Yeah. Okay. All right. So the intention is what? The intention is to somehow provide privacy as well as Byzantine resilience. Now, if we want to use this Krum rule in the context of privacy and Byzantine, somehow we need to bring that into the FL context and ensure that the server gets only this value, which is the distance between the model parameters. Yeah.
If your Byzantine was, I don't know like how it can happen, but is it guaranteed that the Byzantines will be rejected by this? Because what if all my neighbors, we all colluded, so our distance is actually small.
It's
so I get picked up.
Yeah.
Right? It's possible. Right?
Yeah, it's a typical security problem. You have a Byzantine, then you come up with a aggregation rule, and then the Byzantine will actually know the rule because of Kirchhoff's principle, and then they may do something better. So this is sort of a game where they have to settle down somewhere. That's a good point. Yeah.
But is there a guarantee that you will, from here I don't see that how this will be able to rule out the adversaries, right? Because
so
they can actually game it. Yeah.
There are attacks which actually defeat Krum. You design Krum to reject some structure, some kind of anomalies. But then there are attacks called empire attacks where you can design and optimize it, and then they show that basically Krum is going to do very poorly. So Krum is not universally really good or anything like that.
Is this the same idea as robust statistics that you are discarding out?
Yes, yes. It's just that the use case is FL. That's all. That's all. Yes. Okay. Fine. So plugging these things to the FL context, to provide privacy, somehow these users need to reveal only the distance between individual model parameters. But then to provide privacy, they should not reveal Wj and Wk. Okay. You hide the values of Wj, Wk, but only give the distance. So we need to somehow orchestrate a phenomena or sort of some kind of structure like this. Okay. So to do that, we have our contributions. In the next 3 slides, I'm going to give an overview of what we have done without getting into details. And then probably we'll get into details later on. Okay. So point number 1 to note here is that typically the way FL started, users only talk to server, and server talks back to users. Okay. That's why it's called federated. Okay. But then eventually there were generalized models where they also developed a network where users can talk to each other for different reasons, and also along with the server. So these are sort of generalized models for various needs. Okay. What we are going to do in our method is that we will employ the generalized model where users can also talk to each other among them, possibly forming a complete graph. Okay. There are assumptions, but then we are doing that. And then along with that, we also have a server. Okay. Why are we doing that? There's a specific reason. So if you go back to the previous slide, where we have specifically mentioned that we want pairwise distances. Okay. So if you give the values of Wi, Wj to the server, that can compute the pairwise distance, but then we don't want to reveal that, right? So somehow to compute the pairwise distance, somebody should have actually Wi, Wj, so subtract it, right? But then we won't be able to do that because of privacy concerns. So that's the reason we want to have everybody talk to everybody, so that one of the nodes get the values of the other node and then do some kind of subtraction. Okay. So, but what's the trick? The information flow for the users is as follows. Okay. You start off with all the users. These are the blue dots. They have their model parameters. Now what we do is we basically add noise to those model parameters. Okay. And random Gaussian noise, arbitrary. And then they go to the second phase. In the second phase, basically they share this with each other. Okay. And when they do that, basically every node has noisy version of the model parameters of the other users. And then at this particular stage, they compute the difference of every pair, but it's not the WJ WK. They compute the difference of the noisy versions of WJ WK, and then they compute the distance of them, and then send it to the server. Okay. So again, what's happening here is that the users are talking to each other. They compute the distance, not the actual distance, but distance on the noisy versions of their model parameters, and then they send it to server. The algebra with which this is done, can be seen as an equivalent of generating a code word of an underlying analog code. Okay. What's an analog code? It's very similar to our codes over finite fields. It's just that the basis vectors are over r power n, and then you just have to span the space of that, right? So we have a specific code which is based on DFT. It's called discrete Fourier transform code. That's because the generator matrix of this code comes from a subset of a submatrix of the DFT matrix. Okay. So as such, physically these nodes don't pass it through an encoder. The point I'm trying to make is that they do something which generates structure which is as though appearing that like a code word from a DFT code word. That's the point I'm trying to make. Yeah.
Why do this instead of everyone can just send a noisy version of the model to the server and then we can find the difference? Like why do this?
Very good.
Aggregation with each other.
Right. So the idea was to really give a no noisy version of the pairwise distance. If every node, if every user sends a noisy version to the server directly, then the difference will also be noisy, right? And that noisy difference can actually impact the Byzantine resilience, unless it has a way to figure out. No, we will show that it's not possible. Yeah, that's a great point. Okay, so we do all this circus because we want to somehow give the server pairwise distances which has no noise. Okay, this is the flow with the users, and what happens on the other side. So whatever you see in the yellow box and the green box, that's basically the operations happening at the server, right? So these kind of code words basically reach the server. Now, because it has come through sort of code words of analog code, you apply the corresponding decoder to it, and once you decode it, the message symbols of basically that particular code are nothing but the pairwise differences. Again, these are not details, but I'm just only giving you a high-level idea of how it works. And then once you have these pairwise distances, you feed that to Krum. Krum does its job of rejecting outliers depending on the structure, which is typical of what Krum does, right? So that's basically the method, right? So we have and that's basically where analog codes come into picture. So there is privacy preserved because what the server gets is only pairwise distances, but then it doesn't get to see Wj and Wk as it is, and that is the amount of privacy we are providing, and still the Krum operation follows as it is. Okay, all well, but there is a catch. The catch is that when you have Byzantines, and then when you run a protocol over it, Byzantines can actually sort of place spoil sport at every part of protocol, right? So initially, Byzantine resilience is only to ensure that data poisoning attacks are sort of arrested. But now, because you're asking them to also cooperate, some of them are also Byzantines, right? Which means when you ask them to cooperate to perform noisy techniques, they may also inject noise, and they may also disturb it, right? And that they can do because analog codes have inherent noise in them. Because these codes are over real numbers, there are floating point issues. And these floating point issues can be exploited to inject something in this particular phase by the Byzantine users, and then still degrade the effect of Krum, right? That's basically the change highlighting, because we acknowledge that Byzantines can also play spoil sport at the other stages of the protocol. To solve this problem, what we have done is we have come up with a new decoder design in order to arrest any such behavior from Byzantines. And then what we do is there is a way in which the decoder produces likelihood of sort of who is playing spoil sport in terms of soft values, okay? And then what we do is, while we also send the pairwise distances, we also send the soft values on who is misbehaving potentially as side information. And then instead of deploying Krum, we come up with a sort of a modified Krum as a new algorithm where we actually combine the side information from the decoder, and along with the Krum rule, we modify the distances in such a way that you try to do better. Okay, that's basically the overview of what we have done. Yes. In terms of coding theory, what happens is you have a code word, and then there is additive error to it. One of the tasks in coding theory, in a decoding algorithm, is to find out the error location. Okay? Once it finds out the error location, it uses syndrome matrix and then computes the errors and then subtracts it. That's a typical step in coding theory. So error localization is a key step, because if that goes wrong, then the rest of the process also goes wrong. Now, because all the things are happening in floating point, error localization is very delicate. So what we do here is that by localizing the errors, we are also trying to point out who are those possible Byzantines who are misbehaving, because they are the ones who are adding error to the. If you identify localization, so among the 5 nodes, the decoder is going to say that if let's say there are 2 errors, okay, it's going to say that I think most likely with this much probability the noise was added by this particular node. So it is basically pointing at, I think this is one guy who is misbehaving and not following the protocol, right? And now Krum is not doing that. Originally Krum, what it does is only looks at poisoning attacks, but it looks at pair-based instances. So on top of what Krum can do, this decoder is also identifying who is misbehaving. Potentially, if these 2 sets are same, this can actually get improvement over the performance. Okay? So that's basically the strategy here, right? So the novelty is in the way we are designing the decoder in terms of highlighting who is doing wrong things, as well as the way it is combined at the Krum stage in terms of modified Krum. All right. So in terms of analytical contributions, the moment you have a robust aggregator here, right? So typically we want to sort of define goodness of an aggregator in terms of how good it is doing in terms of let's say compared to only when honest users are available, right? So the green arrow that you see is you can think of it as a gradient. Typically, that's how it looks like when only honest users are aggregated, okay? And let's say if you do only Krum without any side information from decoder, that's the red one, which is basically sort of away from the original honest because of the noise added by the Byzantine. So now a good aggregator is the one which basically what it does, it should do is the red one should basically be closer to green, saying that you're still doing good in terms of how close you are to the honest update, right? So typically you study this angle or the distance between these vectors, and then you quantify that and say how good you are doing, right? So in order to do the same thing with our protocol, what we do is the modified Krum, we show that it's at an angle with respect to the honest aggregate, much smaller compared to the vanilla Krum, sort of giving a theoretical guarantee saying that we are indeed doing well by making use of this side information. Yeah, so when we talk about the middle picture, it's only talking about how close are the gradients compared to the honest. But then eventually what happens is this process has to repeat over several iterations in FL, right? And then in the end, what is that we are doing in terms of FL? In any FL process, we want to arrive at a global model that is close to a local minima or a stationary point of the global objective function, loss function, correct? So we still have to show that when we do this, how fast are we converging to stationary point? A bad aggregator can actually help you converge very slowly. A good aggregator will basically converge very fast. Yeah, so picture is something to just show that it is a convergent result, but the result is this, okay? What you see here is basically the rate at which this whole process converges to a stationary point. Now, there are some parameters that I need to define. So T is the number of iterations over which FL works, all right? Sigma square is typically the variance of the noise because of SGD, or the mini batch randomness, all right? And then N is the number of users and F is the number of Byzantine. Basically, N minus F captures the number of honest users ideally that you would want to shortlist, right? And now we have an additional term called K, which is basically coming because of the aggregation rule, which is multi-Krum, okay? Now, if you only focus on the first 2 terms, this is how typically convergence is for a normal SGD without any Byzantine users. This is typically the case, okay? Which means that as you increase the number of iterations, T goes down to infinity asymptotically, and then you go close to the stationary point, okay? But because you have an aggregator, depending on its performance, it also is going to be slowed down a bit. But then this T is also going to multiply as here 1 by T, but then still this K factor will actually slow down the process, right? Now, There is an additional term in our setting. That's mostly because of floating point errors coming because of the real world use cases, right? But then if you have infinite precision systems, then that goes down to 0. Even otherwise, that's a very small number which can potentially neglect. Which one? Right, right. So any amount of poisoning, that can be arbitrary. We don't make any assumptions on that. So the Krum algorithm is going to absorb that. This is the takeaway. Okay. The takeaway is that when we use our modified Krum, the k value is much smaller compared to the vanilla Krum. Okay. So the vanilla Krum is the one which does not take feedback from the decoder, but we give a feedback from the decoder, and that's going to influence in having a value of k much smaller than Krum, which essentially means that if you compare these two point to point, having feedback from the decoder helps us to converge much faster to the stationary point, and then it's a way to sort of theoretically prove. Typically what we do is we run experiments and then we see that it's doing well, wonderful, but then at some point in time we also have to show, sort of prove in theory that it works, and this is basically the rest of the effort in this line. Okay. Just one point before we move into the other details. So in terms of novelty, Salman Avismay group from UCLA, they have been looking at similar problems with security and FL and other things. They had something similar way back in. In fact, my student started reading this paper, and then he was thinking of, he thought about developing our current work. So how does our work differ from the baseline? So basically they had a similar story to say, but then the main difference from their side is that they did not do anything analog. Okay, they were doing everything on the finite field, right? So secret sharing was happening, very similar, but then the entire process of secret sharing as well as recovery at the server was happening on finite fields, which meant that they had to sort of quantize their model parameters to finite fields and do some kind of a recovery of distances and then do the inverse of it for Krum, right? So they sort of used these kind of quantizer and then the inverse of it, which actually creates problems because as long as the finite field is really large, everything is fine. But then large finite fields will also have associated complexity, which makes it really forbiddingly, complexity is really high to really implement this. And that's precisely the reason why we picked up on analog codes. Again, once we use Reed-Solomon codes over the finite fields, soft information is basically is out of the window because there are no such errors. Okay, so that's basically the overview of our contributions. Maybe in the rest of 5-10 minutes, I'll just quickly go through the math. Okay, but I'll not spend too much time. The focus will be on the following. Okay, you have seen 3 things. I think you have to watch out for just 3 things. Number 1. How is secret sharing happening? Because whatever was mentioned was only pictorially. Number 2, how does this analog code come into picture? We'll see the math behind that, 1 or 2 slides. And then number 3 is how the scores are modified by making use of soft information from the decoder. Okay, so let's just do that for the rest of 5-6 minutes. So formally, we call our method as FORTA because this is basically Fourier-based outlier resilient trust aggregation, right? So the point is that we are going to provide both privacy as well as Byzantine resilience for FL, right? And that is already well told. So mathematically, there are n users, f of them are Byzantine. We also have an additional constraint that t of the users may collude in order to sort of infer something about the updates. That's basically the privacy constraint. And then so this is the part where we add noise. Okay, so wi is the model parameter of the ith node, and what the ith user does is it basically creates a polynomial in x. Okay, and then the constant coefficient is basically the model parameter, and the higher degree coefficients are basically random noise. Okay, from let's say from a Gaussian distribution with an appropriately chosen variance. This is partly well known and taken from many prior works of similar type, right? Epsilon I is again precision noise because of analog operations, right? And once this is done, what this user does is basically it evaluates this polynomial over different roots of unity or the nth roots of unity because there are n number of users, and then distributes those evaluations to all the users. So that way that is the way where you're creating noisy model updates, right? And you do that, but one of the points to note here is that the evaluations are done on the nth roots of unity, okay? And this is the point where you're creating a DFT matrix. So when you evaluate the polynomial over omega, omega square, omega cube, and then you can actually write it in form of matrix, then you will see that it's like 1 omega, omega square, and so on. That's where your DFT matrix comes into picture. That's the intuition, and then correspondingly you get a code out of it, okay? Yeah. No. Independent. Yes, yes, yes. They individually pick it up and then they add it. So this method does not require any shared randomness among the users. Correct. When the adversary does something like this or something different, then whatever it adds, right, that can be treated as a noise added to the constant coefficient Wi, right? And Rij's could be 0 there. So you can actually, whatever else the adversary does, you can sort of see it under this framework as a modified version of it. Okay? And then, as you have seen pictorially, these shades. Right. Yeah. So we do it in a controlled manner here because the tool for privacy here is information theoretic. We compute the mutual information. Yes. Yeah. In fact, we have not done a security analysis of what could go wrong in these steps. Something to think about. Okay. So essentially, you have these shares, and then they share it among each other, and then each user computes the pairwise distance on the shared copy, not on the original ones, and then they basically send it out. And this is basically sent to the server. Essentially, what you send is can be seen as evaluation of square of the polynomial here, and then the server gets this type of a collection of vectors for every pair. Okay, and it gets this n choose 2 because you have all possible pairs coming in. So this sends, so user I sends, so let me just go back. Yeah, user I computes, so user I is the one that is having a polynomial. If it has sent to user J, Wj. So evaluation is different for different users.
So basically for all n users I'm going to evaluate n different users.
Correct, correct. And
then in the next slide somehow you
yes.
all the differences.
So now the user I would have actually collected j comma k from the kth and jth user, right? Correct? And that share it already has to itself. So for example, you see.
It's not taking its own difference, it's taking other people.
Yes, yes. It computes a difference, but the share it takes is actually with itself. J sends something to I, it takes sji. K sends something to I, it takes ski, and computes the difference between the two.
Everyone is doing basically everyone else's difference.
It's heavy, yeah. It's heavy in compute. Yes, it's a complete graph. Yes. Okay, and then this user is going to send this, ith user is going to send about jk to the server, and then about jk, the 2 pair, the server gets it from different users, right? So therefore it collects all of them and puts them together. That's why you actually basically get a vector.
So you for JK you get basically from every user one.
N users. Exactly, exactly, exactly. So that is where the correlation is coming in. The same distance between these 2 users, you are hearing from other people. So probably, even if it's not a complete graph, maybe we have not looked at it. If the graph is sparse, or let's say we remove some of the links, we still need to look at the robustness in terms of can we really continue to do this. Yeah, so that's what happens, right? So, and then what we show is that this vector, if you see, this basically is a code word of a discrete Fourier transform code, okay? And then this is just the justification of how it looks like. So eventually, what the server looks at is something like this. So this is the generator matrix of that particular analog code, and then it will have some of the components. But then if you look at the first term on the message, that basically gives the difference between the distance between jth and kth model parameters. All the other values in the vector are irrelevant because they are noise. We don't want to worry about that. Okay. So you apply a decoder, DFT decoder, get back the message, and then in the message has pairwise distance. The RIJs would have actually been observed somewhere here. Okay. These plus are potentially the noise added by the Byzantines.
What about the precision stuff with epsilon?
Along with them. So that addition will also have 2 layers of noise, precision small values, potentially high values with Byzantines.
How does RIJ vanish?
RIJ doesn't vanish. Basically, RIJ is actually in all these things. So what happens is if you go back, all right, and then if you look at this particular term here, every term has RIJs in them, all right, and then if you compute this particular term, it's a polynomial of degree 2t plus 1 or 2t, right? So in this, if you expand, RIJs are basically occupying higher order terms with a lot of cross terms, okay? But the coefficient of the first term is basically only the Wj minus Wk. And that's the reason I mentioned that in this particular vector formulation, only the first term is basically what you want. All the RIJs are absorbed here. It's okay, even if I direct it in a wrong way.
So the stars are RIJ.
Yes, 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 yes. So these are irrelevant, but then these stars are basically noise, potentially from the Byzantines, and then possibly they could be detected appropriately. Okay, so that's a takeaway. So we wanted to really show that how analog codes are coming into play here, and yes.
So we just project to the first dimension and just try to get that because other two matter.
So you know, if there are errors to it, then you basically do the typical decoder for like a Reed-Solomon decoder, right? And then you extract everything, okay, and then you only pick the first component because that's a matter of importance. Okay. Now, by doing all these things, the server is going to recover for every j comma k the pairwise distance. Along with it, it also has a little bit of noise. This is something that is unavoidable because of the precision. Okay. Even though you do a good job in terms of recovery, because of floating point operations, you will still have some noise to it. But then, let's say with 64-bit processor, I think it's still marginal. But then we still want to take care of it in terms of our calculations. Okay. So that point is clear. I'll quickly skip this. This is the flow of how the decoder works. I really don't want to get into this, but then this is perhaps the second most important slide. So what we are showing here is that what we do is when you decode or recover the information at the decoder, we sort of do some kind of counting on who could be basically the Byzantine. Okay, so this is part of the error localization strategy, and then we sort of create these counts and use these counts to feed this into softmax and develop probability values on who could be the Byzantines. Okay, so the decoder says P1, P2 to Pn, and these are my probabilities with which I think this guy is misbehaving or something like that. Okay, sums up to 1, and then you are going to feed that to the Krum. Okay.
So I didn't get this. How do you do this flagging? Maybe because we do the decoder. How, so that code structure, how do you know somebody's misbehaving?
Yes. So what you do is basically there is something called as error localization step. Okay. The way it works is that typically, let's say you fall back on Reed-Solomon codes over the finite fields. From the syndrome matrix, you have the syndrome vectors, all right, and you can actually create something called error locator polynomial. Okay. Now, if you find out the roots of the error locator polynomial, the roots will actually give you the location of the errors. The location of the errors correspond to the identity of the Byzantines. Okay. Now, if it were to be over a finite field, this polynomial has exactly those many roots. But now, these are all noisy polynomials. You don't really look at exact zero evaluations, but then you have to evaluate them, and then you have to do some kind of ordering over real numbers, which means you are developing a likelihood on who could be. So, but then you create this likelihood, store them up, and then create some kind of a count on it, and then eventually end up with a number on Pi. That's what we are going to do. Okay. So once we have these PIs, right, then this is the last trick of the paper or the work, wherein how we are going to sort of modify the scores coming from Krum. Okay, so SI is the score given by Krum for the ith user. We keep it as it is. Okay, but what we are going to do is we are going to sort of translate it appropriately or weigh it by making use of PIs and 1 minus PIs. Okay, so just to give you a context, a higher PI close to 1 means that there's a higher chance of this user being a Byzantine. Okay, so now suppose you have PIs close to 1. That means wherever PIs are 1, I'm not going to disturb the score because I'm keeping the score close to the original score given by Krum. Okay, so wherever the scores are in terms of their distributions, it is still the same. But what I'm going to do is those users which get small PI, which means they appear to be honest, what I'm going to do is I'm going to pull them down and then bring it closer to the minimum value that we have. So you have all the scores, all the users which the decoder thinks as Byzantine, we are keeping their scores as it is. But if the decoder thinks somebody is honest, we are pulling the scores, sort of forcefully separating this cluster from the rest of the users.
I would say PIS max, 1 minus PI, whatever your score is, right?
PIS max, okay.
S max and 1 minus PI.
Yeah. I mean, yeah. So this is actually a heuristic in the sense the way we are combining the Krum score with the soft information, there is no study on the optimality of it. How to really combine them in a way that you formulate a problem and optimize is not clear. But then Usaid came up with this idea, which really started giving good results. And then that we took it on to do some theory behind it. Okay. So I think I'm running a bit late. So this is basically the strategy. And then once the subset is identified, you aggregate these model parameters and then continue the FL process. Okay. In the interest of time, I think I will skip the approach to do the proof. Basically, we are piggybacking on Faradakani's work on something called as F lambda resilience. This is a very standard way to show how good a robust aggregator is. We have followed similar lines, and then we have come up with bounds. Just one point here, we have bounds for our modified Krum as well, but then the main difference here is that we have something called as some R mod is basically a parameter which is coming from the DFT decoder. Okay, so if R mod is equal to 1, okay, that means that all the PI values are identical. Okay, so suppose the decoder says that P1 equal to P2 equal to Pn, which means it's raising the hand saying that I can't do much. I am not able to identify who is the Byzantine. If you do that, then this becomes 1, and then the entire thing falls back to original Krum. Okay, which is supposed to be, because when the decoder says I can't really give you any useful information, then we verify that our bounds also go back to Krum, which is rather intuitive. But then when the decoder says that I have a very strong conviction that somebody is really doing a mistake, then what happens is this R mod will be a value much lower than 1. Okay, and then this value itself comes down, and then based on the resilience definition, we are sort of that angle. You remember, we are going closer to the honest user's case. Okay, that's the gist of the result. I'm not going to the details. We have similar bounds on convergence. Again, for somebody who is working with FL and convergence results, we have followed typical steps. The only catch here is that because we are using precision noise, we also have to compute expectation over the precision noise on top of the stochasticity introduced by SGD. Okay, and this is again a slide to show that when that R mod basically goes to 1, you go back to the K value of Krum. However, if you really have a good decoder and you have a very strong message to the Krum, this really small, you can neglect this, and then the values are really small, and then that basically gives the improvement. Okay. Again, there are experimental results here. We have conducted some results, some experiments based on MNIST and fashion MNIST data sets to compare what happens when there is a feedback and without feedback. These results indicate that significant there is remarkable improvement between for using the feedback or rather some side information from the decoder. Okay, so just to conclude, just 3 slides. This is the big picture. Okay, now we have an analog code-based strategy to provide privacy as well as Byzantine resilience. All right. Now, original job of Krum is to arrest any poisoning of sort of attacks, right? So, if I have this symbol against this, this means that this is basically poisoning. Okay. So, if poisoning is done on the data sets, then there is some issue, and when the whole flow goes through fine, the performance is as good as vanilla Krum, and with a little bit of precision effects because of floating point. Okay. But if the Byzantines also start behaving badly, not just by poisoning, by also they behave poorly, let's say by not adhering to the protocol, we can detect that, right? And so basically, if you don't detect that, right, and continue with the same thing, the consequences are this: the results will actually be worse than the vanilla Krum because you're going to degrade, right? And then you're going to have poor performance, right? So in order to correct this, we sort of fix this by having a new decoder which feeds some information to the Krum algorithm, and when we do this, we have basically seen that the performance is better than the vanilla Krum with negligible precision noise effect. Okay, that's because of having multiple code words. With that, I'm going to end this. I don't have any more slides. It's 55. Okay, so any questions?
Thank you, Professor Harshan, for accepting our request and delivering an interesting talk. Any questions?
Hey, good question. It's missing. Maybe I have put a pause. No. Pause doesn't increase the slide count. Good one. So I kept you on your toes expecting what is going to come next. You had something.
Yeah, I have a very nice question. So what would you expect if n goes to infinity? What should happen to the bounds?
So even if n goes to infinity, yes, the question is what do you want to do with f? If you want to keep f same,
yeah, f is same.
So f is same, then that means you are having majority of good results. Yes. Then results will improve. So you can just plug it in here.
But shouldn't the errors go to 0 in that case?
No, because Byzantines will, the aggregation technique is still not perfect.
Suppose f is also 0.
So yeah, f is 0, then of course, so if f is 0, yeah, in the Fed averaging setting with honest users, yes, the number of users come in a denominator along, yes, with the number of iterations. Yes. So it goes down as 1 by square root of n.
Yeah, but there was an additive term which was a constant.
Correct. That constant is actually going to define the goodness of the aggregation method. Okay. And if you go back and see the Krum one, that constant will actually have n minus f in it. I see. Okay. So although the first term goes down because of original Fed averaging, this n basically prevents it from going down to 0. That's basically the problem with the aggregation method.
Thanks.
There are two terms, right? And one of them was sigma square kappa by
correct.
T. I think that kappa is not going to
K is not going to 0. Yes.
One arbitrary question. Does there exist a minimum n for which the number n of Byzantine agents who could convince the server that they are the legit?
Are you asking bound on f?
Yeah.
So f has to be less than n by 2. We need to have majority of honest users in the system to work. So when we do asymptotic analysis, we drag f. When we increase n, we also increase f to a certain extent that, just to see what happens to the overall ratio. But then we always want f to be less than n by 2. Otherwise, the results are diverging. We don't get good results.
And this is like
this is everywhere, even in blockchains. Right. So we want system to have majority of good, honest, good users.
And in such a case, does the dropping of these updates, say like coming to Ganesh's point of fully connected graph. So if you could arrange for some updates to be blocked, does that change the results?
Yeah. So the notion of robustness is that in one round, if there are some misbehaving nodes, okay, I perhaps take them away from aggregation. but in the next round, I'm not calling them not to participate. So we'll continue to sort of have them in every round. And the other strong assumption is that in the next round, the set of F users can change. I'm not assuming that the same set of F users continue to appear. If there is some kind of a memory to this, then what we could perhaps do is the information that we get in round number 1, we could basically carry it over to the second round and then build that up and then get really good results. But that's a strong assumption. So typically what we do is when we say F Byzantine users, the next round it can be any other F, but maximum is F. So that's actually a really good assumption to work with.
And the small question, like, does the modified Krum make it worse in terms of stability, in terms of like these colluding Byzantines?
What do you mean by stability?
This your assumption of n by 2, right?
Sure.
So can they craft these localization messages to like convince the server even with less than n by 2?
Yeah. So in fact, so we are not claiming that this is universally good. The next step here is that you have this method, then the Byzantines can actually optimize, come up with a strategy to even deceive this modified Krum. In fact, for the vanilla Krum itself, there are attacks called as empire attacks, where you give all the information. They'll basically craft the updates in a certain direction in such a way that even Krum fails. So something similar can be done even with modified Krum. Again, this is actually an evolving problem, which is very typical in any security topic.
Any more questions? Okay, thank you, Professor, for the talk. Thank you, everyone, for attending. Refreshments are arranged in the coffee hut. Please help yourself.
Thank you.